3 months ago, the seismographs at Yellowstone began recording something the volcanologists had never seen before. Not the familiar earthquakes that ripple through the park every week, but a low-frequency signal, almost rhythmic, emanating from 12 miles below the caldera floor. Within 48 hours, thermal satellites detected a 2.7 degrees Fahrenheit temperature increase in the Norris Geyser Basin. The ground itself was breathing differently. 5 separate monitoring stations confirmed the same impossible reading. The magma chamber wasn't just shifting, it was pulsing. The instruments had been watching Yellowstone for decades, built to catch the warning signs of an eruption, but these signals didn't match any known precursor pattern. They were older, deeper, coming from a place the sensors weren't designed to reach. By the time the USGS convened an emergency consultation, the data had already rewritten what scientists thought they understood about the caldera's behavior. But to understand what that change actually means, you have to go back to the moment Yellowstone was born. The hotspot. Beneath Yellowstone, 400 miles down, a plume of superheated rock rises from near the boundary between Earth's mantle and its molten core. It's a column of heat, stationary in the planet's interior, while the North American plate drifts southwest over it at 1.5 inches per year. For the last 17 million years, that plume has burned through the crust like a blowtorch held beneath a sheet of wax. The Snake River Plain stretches 400 miles across southern Idaho, a scar of calderas marking each place the continent paused above the heat, each one now cold, collapsed, filled with sediment. The hotspot doesn't move. The continent does. Every eruption leaves a caldera behind as the plate slides on, and a new one forms where the plume breaks through again. Yellowstone is simply the current expression of a process that began when the Pacific Northwest looked nothing like it does today. You can trace the plume's path backward through time, caldera by caldera, all the way to the Columbia Plateau in eastern Oregon, and the caldera we see today is only the most recent wound in that chain. The Three Sisters. Yellowstone has erupted catastrophically 3 times. The first, 2.1 million years ago, ejected 588 cubic miles of ash and rock, creating the Island Park caldera. The second, 1.3 million years ago, released 67 cubic miles and formed the smaller Henry's Fork caldera. The third eruption, 640,000 years ago, expelled 240 cubic miles of material and carved out the caldera that defines the park today. Ash from that event blanketed half the continent. Layers 6 feet deep have been found in Kansas. Traces appear in sediment cores pulled from the Gulf of Mexico. Each eruption triggered a volcanic winter, sulfur aerosols reflecting sunlight back into space, dropping global temperatures by 5 to 10 degrees Fahrenheit for years. Forests died, ice sheets advanced, then the ash settled, the skies cleared, and life crept back into the scorched basins. The interval between eruptions averages 700,000 years, but geologists stopped relying on that number decades ago. What nobody expected was how different each eruption's signature turned out to be. The caldera floor. The caldera itself stretches 30 miles east to west and 45 miles north to south, a collapsed crater so vast you can't see the rim from the center. Most visitors see only forests, meadows, and the steam plumes of geysers. The ground looks stable, even gentle. But beneath that surface lie 2 resurgent domes, Sour Creek to the northeast and Mallard Lake to the southwest, each the size of a small mountain range. They've been rising for thousands of years, pushed upward by magma that never quite breaks through. Between 2004 and 2010, the ground near Sour Creek lifted 3 inches per year, faster than almost any volcano on Earth. Then the uplift slowed. By 2015, parts of the caldera were sinking again at nearly the same rate. The domes breathe, geologists say, swelling and subsiding as fluids migrate through the crust. But inflation alone doesn't tell you when or if an eruption is coming. The magma below. Seismic tomography reveals two reservoirs stacked beneath the park. The upper chamber sits 3 to 9 miles down, a body of rock and crystal roughly the size of Los Angeles. Only 5% to 15% of it is molten at any given time. The rest is mush, hot enough to glow, but too viscous to flow. Below that, between 12 and 30 miles deep, lies a second reservoir 4.4 times larger. It holds perhaps 2% melt, the rest locked in a matrix of solid rock laced with pockets of magma no bigger than swimming pools. Together, the two chambers contain enough eruptible material to fill the Grand Canyon 11 times over, but most of it would need to liquefy first. Eruptions happen when fresh magma intrudes from below, heating the mush until enough of it melts to become buoyant. The process takes centuries at minimum, often millennia, and that solid state is exactly what made the new readings so strange. The seismic network. The University of Utah Seismograph Stations operates 53 permanent seismic stations around Yellowstone, each one recording ground motion 24 hours a day. GPS receivers track horizontal and vertical displacement down to fractions of an inch. Tilt meters measure changes in the slope of the ground, and gas sensors sample the chemistry of fumaroles and hot springs. The system logs between 1/500 and 2,500 earthquakes per year, most of them magnitude 2 or smaller. A handful reach magnitude 3, enough to rattle dishes in nearby towns. Swarms are common, clusters of dozens or even hundreds of quakes in a single week, usually tied to fluid movement in the shallow crust. Seismologists review every event, sorting tectonic shifts from hydrothermal noise, cataloguing depths and magnitudes. The data flows into public dashboards updated in near real time. What changed in late 2024 wasn't the number of quakes, it was where they were clustering. The swarm begins. On October 12, 2024, the first tremors registered beneath Norris Geyser Basin. Within 24 hours, 40 more followed. By the end of the week, seismometers had logged 183 separate events. Over the next 6 weeks, that number climbed to 2,347 quakes. Most fell between magnitude 1.2 and 2.4, too small to feel on the surface, but sharp enough to pinpoint their origin. The cluster sat directly under Norris, the hottest and most volatile thermal area in the park. Swarms like this happen at Yellowstone every few years. The caldera is restless by nature, its crust fractured and soaked with pressurized water. What made this sequence different wasn't the frequency, it was the geometry. Seismologists noticed the hypocenters weren't staying put, they were moving. Pay attention to this next detail because it explains everything that followed. The depth anomaly. The first quakes originated 8 miles below the surface. By late October, new events were nucleating at 7 miles. By mid-November, the focal depths had shoaled to 5 miles, then 4. This wasn't random scatter. The swarm was migrating upward through the crust, following a near-vertical path. Tectonic earthquakes don't behave that way. They rupture along faults, releasing strain that's built up over years. But these quakes were lighting up in sequence, one above the other, as if something was pushing through the rock. The pattern pointed to fluid movement, probably superheated water forcing its way through fractures in the hydrothermal system. Scientists logged it as enhanced circulation, a known process at Norris. The basin sits on a major fault intersection where groundwater can drop deep, heat up, and rise again. It was a plausible explanation, but the gas readings told a different story. The helium spike. Fumaroles around Norris vent steam and volcanic gases 24 hours a day. Researchers sampled them weekly, measuring isotope ratios that reveal where the gases originated. In early November 2020, the helium-3 to helium-4 ratio jumped 18% above baseline. Helium-3 is rare on Earth. Most of it escaped into space billions of years ago. The only terrestrial source that still produces it in meaningful quantities is the mantle, 40 miles down, where the Yellowstone plume begins. Crustal rocks and groundwater contain almost no helium-3. When it shows up in surface vents, it means fresh magma or mantle-derived fluid has reached the upper crust. The spike at Norris indicated a new pulse of deep material had entered the system. By December, concentrations had climbed another 9%. The timing matched the earthquake migration exactly. Whatever was rising through those fractures wasn't just water, and that wasn't the only gas behaving strangely. The carbon shift. Carbon dioxide was climbing too. At Norris Geyser Basin, emissions jumped 22% over baseline. Mud Volcano, 9 miles south, recorded a 14% increase. The readings arrived within 48 hours of each other. Gas spectrometry told the rest. The carbon's isotopic signature didn't match limestone decomposition, the usual source in hydrothermal systems. This CO2 carried the fingerprint of magma, rising from depth. The flux numbers suggested something had opened a pathway between the deep reservoir and the surface plumbing. Two noble gases spiking at once, a magmatic carbon surge, and 400 earthquakes all pointing to the same narrow corridor beneath the caldera floor. The pattern was too coordinated to be coincidence. What comes next is the part seismologists are still arguing about. The harmonic tremor. On December 4, 2024, seismometers across the network began recording something different. Not sharp quakes, but a continuous low hum. The frequency held steady between 1 and 5 Hz. A vibration felt more than heard. It lasted 11 hours without stopping. Seismologists call it harmonic tremor. It's the signature of fluid forcing its way through rock, pushing open fractures as it moves. At volcanoes, it means one of two things: pressurized water surging through the hydrothermal system, or magma migrating upward. The waveform alone can't tell you which. 3 stations triangulated the signal simultaneously. The amplitude was weak but unmistakable, the kind of tremor that shows up in textbooks before eruptions at Kilauea or Mount St. Helens. Yellowstone had produced brief tremor episodes before, always tied to geyser basins or shallow steam. But the tremor's source wasn't where anyone expected it to be. The deep source. The triangulation pointed down. 14 miles beneath the surface, deep in the crust, where temperatures reach 1,570 degrees Fahrenheit. That put the source squarely inside the lower magma reservoir, the vast melt zone that feeds Yellowstone's entire volcanic system. Tremor from that depth is rare. Hydrothermal systems sit in the top 3 miles. The upper magma chamber, which last erupted 640,000 years ago, sits at 5 to 9 miles. But 14 miles down is the deep plume, the boundary where mantle rock begins to melt. Movement there means the foundational heat source is shifting. No instrument at Yellowstone had ever cleanly recorded tremor from the lower reservoir before. The signal was faint, easily drowned out by wind or traffic. But the December event was strong enough to persist through noise. Whatever moved down there moved in volume, and it moved for half a day. And the ground above it was starting to respond. The uplift pulse. The GPS stations had been watching the caldera surface for decades, measuring movement down to the millimetre. By mid-December 2024, the Sour Creek Dome had risen 2.1 centimetres in 3 weeks. That was the fastest uplift rate since 2014, when the caldera pushed upward for 18 months before settling back down. Uplift pulses are normal at Yellowstone. The caldera breathes, rising and falling as magma and hydrothermal fluids shift in the reservoir below. Most cycles last months or years, a slow inflation followed by equally slow deflation, and none of them have ever led to an eruption. But this pulse was different. It started exactly when the deep harmonic tremor began, December 3rd, and accelerated through the month. The timing wasn't a coincidence. Something was pushing up from below, and the surface was responding in real time. What nobody could agree on was whether this was the start of something or the end. The historical record. Yellowstone's modern uplift record goes back to 1923, when surveyors first noticed the caldera floor rising. Between 1923 and 1984, the ground climbed 72 centimetres, then sank 14 centimetres by 1995. It rose again from 1995 to 2003, dropped until 2007, then pushed upward through 2014. Each cycle lasted years, sometimes a decade. Each one moved the caldera floor by tens of centimetres, sometimes more, and each one eventually reversed, the dome sinking back as pressure redistributed through the magma reservoir and hydrothermal system below. None of them led to an eruption. Geologists call it caldera breathing, the slow expansion and contraction of a massive volcanic system that's never quite at rest. It's what supercaldera systems do, a rhythm as predictable as tides. But this time, the breathing had changed rhythm. The tilt data. The borehole tilt meters sit deep enough to filter out weather and thermal noise, measuring the angle of the ground to within a microradian. By late December, the Norris station was tilting northeast at 3.7 microradians per day. Sour Creek was tilting south-southwest at 4.2 microradians per day. The deformation wasn't symmetric. If the entire magma reservoir were inflating, the tilt vectors would radiate outward from the centre, a broad dome rising evenly across the caldera. Instead, the geometry pointed to something smaller, more localised, a point source. The models suggested a dike or a small magma batch rising from depth, pushing upward along a narrow conduit. The angles implied it was somewhere beneath the Sour Creek dome, maybe 8 to 12 kilometres down, shallow enough to deform the surface, but deep enough to stay hidden from direct observation. And the thermal satellites were picking up something the ground sensors couldn't see. The heat signature. Landsat 8 crossed over Yellowstone on January 9, 2025. Its thermal infrared sensor scanning the winter landscape in 11 wavelength bands. The data showed a patch of ground at Norris Geyser Basin glowing warmer than it should. Surface temperatures in a 200-metre zone of Porcelain Basin were running 3 to 5 degrees Celsius above baseline, a sustained anomaly that hadn't been there in December. MODIS, on the Terra satellite, confirmed it 3 days later. The heat wasn't coming from a single feature like a geyser vent. It was diffuse, spread across a broad area, as if the ground itself had begun radiating from below. Park geologists walked the basin with handheld infrared cameras and found new steam vents opening along fractures that had been dormant for years. The pattern suggested hydrothermal fluids rising through freshly opened pathways, driven by pressure changes deeper in the system. Water that had been circulating at depth was now finding routes closer to the surface, carrying heat with it. The timing matched the tilt reversal and the helium spike. What came next made the USGS issue its first formal update in 2 years. The advisory. On January 17, 2025, the Yellowstone Volcano Observatory posted a statement to its public monitoring page. It acknowledged the earthquake swarm, the 2.1 centimetres of uplift at Norris, the elevated helium-3 ratios, and the thermal anomaly in Porcelain Basin. It restated that there were no signs of an imminent volcanic eruption and that alert levels remained at normal background status. Then came the sentence that spread across every geology forum and newsfeed. Current observations indicate an ongoing magmatic hydrothermal disturbance of unusual character. The word magmatic confirmed that molten rock was involved. Hydrothermal meant the plumbing was responding. Unusual character was the part that stood out, because the observatory rarely used qualifiers like that. The statement didn't specify what made it unusual or how it differed from past swarms. It didn't offer a timeline or a forecast. It simply acknowledged that something was happening beneath Yellowstone that didn't fit the standard patterns they'd seen in 40 years of modern monitoring. The careful language raised more questions than it answered, because the word unusual meant something specific to the scientists who wrote it. The model problem. Yellowstone has erupted 3 times in the last 2.1 million years. The first explosion, 2.1 million years ago, left the Island Park caldera. The second, 1.3 million years ago, formed the Henry's Fork caldera. The third, 640,000 years ago, created the caldera we see today. No written records exist for any of them. No seismic network was there to capture the build-up. Most of what volcanologists know about super-eruptions comes from the deposits they left behind, ash layers and ignimbrite sheets analysed decades or centuries later. Real-time monitoring of a supervolcano during an active intrusion event is vanishingly rare. Yellowstone's modern seismic network has only been operating since the 1970s, and in that time the caldera has never done anything close to what precedes an eruption. The scientists watching the data in January 2025 had no historical template to compare it against. They had models built from smaller volcanoes, from Mount St. Helens and Pinatubo and Eyjafjallajökull, systems that erupted on human timescales with instruments watching. But Yellowstone operates on geologic time, and its size makes it fundamentally different. Every sensor, every gas ratio, every centimetre of deformation was being measured against a baseline with no known endpoint. And every other supervolcano on Earth complicates the picture further. The global analogues. Campi Flegrei, outside Naples, has been rising since 1950. The ground there has lifted more than 3 metres in some places, pushing the harbour upward, cracking buildings, forcing evacuations. It last erupted in 1538, and before that 39,000 years ago, when it blanketed Europe in ash. Toba, in Indonesia, went silent 74,000 years ago, after an eruption so massive it left a crater 100 kilometres long. The caldera is now a lake, ringed by peaks. Seismic stations record almost nothing. No swarms, no deformation, no gas anomalies. Taupo, in New Zealand, last erupted in 232 CE, a blast that darkened skies across the southern hemisphere and carved new bays into the lake's shoreline. Today, it inflates and deflates on decade-long cycles, the ground breathing without pattern. Some calderas swell for centuries and never erupt. Others give hours of warning. But one of them gave scientists a clue about what might be happening at Yellowstone. The Taupo clue. In 2019, a team at GNS Science in New Zealand reconstructed the months before Taupo's 232 CE eruption using lake sediment cores and Maori oral histories. The cores showed a sharp increase in fine ash and microquakes starting roughly 20 years earlier, then accelerating in the final decade. The oral histories described the ground shaking, hot springs appearing in places that had been dry, the lake level dropping as magma absorbed water from the hydrothermal system below. All of it pointing to deep intrusion, magma rising from a lower chamber and pooling beneath the surface. The surface unrest became obvious only in the final 3 years. Before that, the signs were subtle: scattered earthquakes, slow uplift, gas vents shifting temperature. By the time the caldera began to swell dramatically, the magma had already been ascending for decades. And the timeline was uncomfortably similar to Yellowstone's recent activity. The intrusion hypothesis. By early 2025, a working hypothesis had formed among researchers at the Yellowstone Volcano Observatory. The helium spike, the carbon shift, the harmonic tremor, all of it suggested a small batch of fresh melt ascending from the lower magma reservoir at 12 to 28 kilometres depth toward the upper chamber at 5 to 10 kilometres. The volume was uncertain, maybe a few cubic kilometres, enough to explain the seismic and gas signals, but far too little to trigger an eruption. The ascent itself could take years, the magma stalling at depth, crystallizing, losing heat. It might never reach the surface. But the intrusion would pressurize the upper chamber, force fluids through fractures, heat the hydrothermal system from below. The caldera would continue to deform, slowly at first, then in pulses as pockets of melt pushed upward and stalled again. The pattern could last decades. But even if it doesn't erupt, the intrusion itself could change the caldera permanently. The hydrothermal trigger. There's a second way this story could turn dangerous, one that doesn't require a single drop of magma to reach the surface. Yellowstone sits atop the largest hydrothermal system on Earth, a sprawling network of superheated water and steam locked under pressure in fractured rock. When rising magma pushes into that system, it doesn't just heat the water, it compresses it. The temperature climbs past 400 degrees Fahrenheit, sometimes higher, but the pressure keeps it liquid. If that pressure drops suddenly, a crack opens, or the rock above shifts, the water flashes to steam in an instant. The expansion is violent. What was confined becomes explosive, blasting through hundreds of feet of rock and soil in seconds. These are called phreatic explosions, steam-driven blasts that can carve craters a mile wide and hurl boulders the size of cars across the landscape. No lava, no ash cloud, just water turning to steam with enough force to reshape the ground. And the historical record shows it's happened before. The explosion craters. Mary Bay, on the northern edge of Yellowstone Lake, is 1.5 miles across. It formed 13,000 years ago when a hydrothermal explosion tore through the caldera floor, ejecting an estimated 8 million cubic feet of rock and sediment. The crater it left behind is 160 feet deep. Elliott's crater, west of Old Faithful, punched a hole 700 feet wide. Pocket Basin, near West Thumb, is another scar from the same process. These weren't volcanic eruptions. They were ruptures in the plumbing. Pressure built in pockets of superheated water trapped beneath layers of silica-sealed rock, then released all at once. The ground above didn't subside. It exploded outward, scattering debris for miles and leaving behind bowl-shaped depressions that filled with water or became thermal features. Researchers have mapped more than a dozen of these craters across the park, some hidden under forests, others submerged beneath lakes. The energy required to create them is staggering, equivalent to detonating thousands of tons of TNT in a fraction of a second. What nobody knew until recently was how often they actually occur. The frequency study. In 2018, a team led by the USGS published a survey of hydrothermal explosion deposits at Yellowstone, combining core samples, radiocarbon dating, and thermal imaging to reconstruct the timeline. They identified at least 25 large explosions in the past 14,000 years. That works out to roughly one every 560 years. The most recent happened around 1300 CE, in the area now covered by Yellowstone Lake. 7 centuries have passed since then. Statistically, the park is overdue. The study found no correlation between hydrothermal explosions and volcanic eruptions. They're independent events. A crater can form tomorrow without the magma chamber stirring at all. But the researchers noted one consistent factor across past blasts: changes in ground pressure. Uplift, subsidence, fault movement, anything that shifts the stress balance in the subsurface plumbing can destabilize a pocket of superheated water. Right now, Yellowstone is experiencing all three. The caldera floor is rising, faults are slipping, and seismic swarms are rattling the hydrothermal zones. And the current unrest might be exactly the kind of pressure shift that sets one off. The park response. The Park Service didn't panic. They adjusted. Ranger patrols around Norris Geyser Basin doubled in frequency, watching for sudden changes in steam output or ground temperature. Trails near Mud Volcano were closed when soil temperatures climbed past 200 degrees Fahrenheit, hot enough to melt boot rubber. New signs appeared at thermal features explaining that the earth beneath Yellowstone is restless, that swarms and ground shifts are part of the caldera's rhythm. The message was careful, calibrated. Vigilance, not evacuation. Awareness, not alarm. Scientists briefed park staff on what to watch for. Abrupt colour changes in hot springs, trees dying in clusters from underground heat, new fractures opening in pavement. These would be early warnings of hydrothermal shifts, not necessarily magma, but worth tracking. The monitoring intensified, quiet and methodical. But the question visitors kept asking was the one nobody could answer. The eruption question: will it erupt? And if it does, what kind? The statistical answer is cold comfort. The USGS puts Yellowstone's annual probability of a supereruption at 1 in 730,000. Roughly the same odds as a large asteroid impact. Far more likely is a smaller lava flow, maybe 1 in 10,000 per year, or a hydrothermal explosion. The current unrest doesn't move those numbers much. Swarms and uplift happen every few years. Most die out. The caldera has risen and fallen 10 inches at a time without erupting. Probabilities smooth over the noise, turning decades of data into a single, reassuring fraction. But they also flatten context. They tell you what's typical across centuries, not whether this particular episode is different, not whether the magma chamber is stirring in a way it hasn't before, not whether the intrusion detected in 2014 is still growing, still pressurizing the system from below. But statistics don't tell you what's happening right now, 14 miles beneath your feet. The magma ascent. If magma is rising, it moves the way syrup climbs through cold honey. Buoyancy drives it upward, hotter and less dense than the surrounding crust. It squeezes into fractures, prying open pathways grain by grain. The ascent is slow, measured in centimetres per day at best, years or decades for a large intrusion to migrate from deep reservoir to shallow chamber. As it climbs, it cools. Crystals form, olivine and plagioclase locking into solid lattices. That crystallization releases dissolved gases, water and carbon dioxide and sulfur, which bubble out and increase pressure. The melt becomes more buoyant, more explosive. The process feeds itself, a feedback loop between cooling and gas release. If the current batch is moving, it's creeping. Seismic imaging can't resolve motion that subtle. You infer it from surface clues: the swarms, the tilt, the heat. The magma might be pooling somewhere in the mid-crust, stalling as it loses momentum, or it might be inching upward, molecule by molecule, toward the base of the shallow reservoir. And the journey from deep reservoir to surface is a gauntlet of obstacles. The crystallization barrier. The first obstacle is the chamber itself. The upper reservoir isn't a lake of liquid magma. It's a crystal mush, a sponge of interlocking minerals with melt trapped in the gaps between them. 5 to 15% liquid by volume, the rest solid rock. When fresh magma arrives from below, it enters this rigid lattice. To rise further, it must either melt the crystals in its path, which requires enormous heat, or stall and cool, adding its own minerals to the mush. Most intrusions do the latter. They freeze before they breach the surface. The chamber grows denser with each failed attempt, layer upon layer of solidified magma building over millennia. The oldest crystals in Yellowstone's mush are 250,000 years old. But if enough melt accumulates, the mush itself can remobilize. The melt threshold. The threshold is a matter of geometry. When the liquid fraction reaches roughly 50%, the crystals lose their grip on one another. The rigid lattice becomes a slurry, and the entire mass can move. Yellowstone's current chamber sits at 5–15% melt. To cross 50%, you'd need a massive injection of new magma, hot enough to dissolve the surrounding crystals, or sustained external heating over long timescales. Either scenario requires heat flux orders of magnitude above what the caldera delivers today. The GPS network shows no sign of the rapid uplift you'd expect from a large intrusion. The seismic data reveals no magma conduits opening through the crust. The mush remains locked in place. and the current signals suggest neither is happening yet. The timescale debate. How long does it take to wake a supervolcano? The models disagree. Some suggest centuries of sustained intrusion, a slow accumulation of heat and melt that eventually tips the system toward eruption. Others point to evidence that the final assembly can happen fast. Zircon crystals from Yellowstone's last super-eruption 640,000 years ago preserve a record of temperature changes in their crystal lattices. Some analyses suggest the chamber reheated and mobilized in less than 500 years. Other studies argue for longer timescales, thousands of years of gradual warming. The difference matters. Centuries give you time to prepare. Decades force you to reckon with a threat that could materialize within a human lifespan. The debate hinges on how fast magma can travel through the crust and how efficiently it can melt the overlying mush. What comes next is the data that might settle the debate. The zircon clocks. Zircon crystals form inside magma chambers, and they grow like trees, adding rings as conditions change. Each ring locks in a chemical signature that tells you the temperature at that moment in time. Geologists extract zircons from Yellowstone's ash deposits and read them backward, reconstructing the thermal history of the chamber in the centuries before it erupted. What they found in multiple eruptions is a two-stage pattern. The crystals spent tens of thousands of years sitting in cold mush below 750 degrees Celsius, a temperature too low to mobilize magma. Then, in the final few centuries, sometimes decades, the temperature spiked rapidly past 800 degrees Celsius as fresh magma injected from below. The heating wasn't gradual. It was fast enough that the outer rings of the zircons show abrupt compositional changes, meaning the mush went from stable to eruptible in a geological blink. And the heating pattern matches what geophysicists are seeing right now. The melt lens. In 2015, seismic tomography detected something new beneath Norris Geyser Basin. A thin horizontal layer, 6 miles across and only a few hundred meters thick, sitting 3 to 9 miles below the surface. The seismic waves slow down as they pass through it, which means the rock is partially molten. The team calculated a melt fraction around 9%, higher than the surrounding mush. That makes it the most eruptible zone currently known in the system, a lens-shaped pocket where magma could accumulate and pressurize. It's not large enough to feed a super-eruption on its own, but it's a weak point, a place where the crust is already starting to fail. The layer sits directly beneath the area with the highest heat flow, the most aggressive hydrothermal activity, and the fastest ground uplift. It's the engine driving the surface changes that tourists see every day. And the recent earthquakes are happening directly above it. The fault connection. On August 17, 1959, the ground 20 miles northwest of Yellowstone tore open along the Hebgen Lake Fault. The magnitude 7.3 earthquake dropped the north shore of the lake 19 feet in seconds, triggered a landslide that buried a campground and killed 28 people, and sent seismic waves rippling through the caldera. Within days, new geysers began erupting inside the park. Dormant hot springs reactivated. Ground temperatures spiked in areas that had been stable for decades. The quake had shaken the plumbing system, opening new fractures and rearranging the pressure balance in the hydrothermal network below. Seismologists assumed the disturbance would fade as the system re-equilibrated. But GPS data collected decades later showed something else. The uplift at Norris never returned to its pre-1959 rate. The earthquake had shifted the magma system into a new configuration, one with a slightly higher baseline of unrest. But what scientists discovered decades later was that the disturbance never really stopped. The stress transfer. When a fault ruptures, it doesn't just shake the ground. It redistributes stress across the crust, loading pressure onto nearby faults and any magma chambers in the vicinity. The 1959 Hebgen Lake earthquake transferred stress directly into the Yellowstone system. Geophysicists modelling the event found that the quake increased Coulomb stress beneath the caldera by 0.01 to 0.1 megapascals. That's small in absolute terms, but enough to nudge a pressurized magma body closer to failure. The uplift that began 5 years later may have been the delayed response. Tectonic stress and magmatic unrest aren't independent variables. They're coupled through the same network of faults and fractures that cut through the crust. A quake 40 miles away can change the pressure distribution inside a volcanic system, opening pathways for magma or hydrothermal fluids to move. And the region is still seismically active in ways that matter. The Teton Fault. 60 miles south of Yellowstone, the Teton Fault runs along the eastern base of the Teton Range. It's a normal fault, 44 miles long, capable of producing magnitude 7+ earthquakes. The last major rupture happened somewhere between 4,800 and 7,000 years ago, raising the mountains another 6 to 10 feet in a single event. Paleoseismic trenches show evidence of at least 5 large quakes in the past 15,000 years. The recurrence interval is roughly 2,000 to 4,000 years, which means the fault is statistically overdue. A magnitude 7.5 quake on the Teton Fault would be felt strongly across the Yellowstone caldera. The stress transfer from an event that size could increase pressure beneath Yellowstone by several times what the 1959 quake delivered. It could rupture hydrothermal seals, trigger swarms, or accelerate an ongoing magmatic intrusion. What nobody wants to imagine is a big quake happening during a magmatic intrusion. The coupled hazard. In 2021, researchers modelled exactly that scenario. A magnitude 7 earthquake on the Teton Fault during a period of high magmatic unrest. The results showed that the combined stress could rupture pressurized hydrothermal reservoirs beneath Yellowstone Lake, triggering phreatic explosions. It could also destabilize a rising dike, forcing magma toward the surface faster than it would otherwise move. The probability of the two events coinciding is low, somewhere below 1% in any given century. But the consequences would compound in ways that neither hazard produces alone. A quake wouldn't cause an eruption on its own, but it could push an already unstable system past a threshold. The study didn't predict when or if this might happen. It simply quantified the coupling between tectonic and volcanic hazards in the region. And the current unrest is unfolding in exactly that tectonic setting. The monitoring gaps. The instruments tell us the chamber is restless. They measure ground motion, gas chemistry, seismic velocity, but they can't see inside. Seismic waves travel through rock and magma at different speeds, revealing density contrasts. But they can't distinguish between partially molten mush and solid crystal frameworks with a few % melt. The difference matters. Gas measurements sample only what reaches the surface through fractures and vents. Deep pockets of pressurized magma may release nothing until the moment they breach containment. GPS tracks millimeters of uplift, but tells you nothing about the fluid distribution 6 miles down. For decades, scientists have inferred the chamber's state from indirect signals, piecing together a picture from echoes and shadows. But one new technology is starting to change that. The muon detectors. Muons are subatomic particles created when cosmic rays collide with the upper atmosphere. They rain down continuously, penetrating rock like X-rays through tissue. Dense material absorbs more muons. By counting how many particles pass through a mountain or a magma chamber, you can map density variations inside without drilling. The technique is called muon tomography. In 2023, a collaboration between Los Alamos National Laboratory and the USGS deployed prototype muon detectors at 3 sites around Yellowstone. Each detector is a stack of scintillator panels that flash when a muon passes through, recording its trajectory. The detectors have been collecting data for 18 months now, building up a statistical image of what lies beneath Norris Geyser Basin. And the first results are starting to arrive. The density map. The The preliminary muon data, released in early 2025, show a small high-density anomaly at 8 kilometres depth directly beneath Norris. It's roughly 2 kilometres across. High density could mean melt-rich magma, denser than the surrounding crystal mush. Or it could be hydrothermally altered rock, minerals recrystallised by hot fluids over thousands of years. The current resolution isn't fine enough to distinguish between them. But the anomaly sits exactly where seismic tomography detected a low-velocity zone in 2019. It aligns with the source region of the 2023 tremor swarm. GPS shows maximum uplift directly above it. 3 independent methods pointing to the same 8-kilometre pocket. The muon team is deploying 4 additional detectors this summer to refine the image. What comes next is the question scientists have been avoiding in public. The eruption forecast. No volcanic system on Earth has been studied more intensely than Yellowstone, and yet scientists still can't tell you when it will erupt. There's no historical baseline. The last super eruption happened 640,000 years ago, long before seismometers, GPS networks, or satellite monitoring existed. The precursor signals could unfold over decades or compress into weeks. The magma chamber might destabilize gradually, or a distant earthquake might trigger runaway decompression. Every model requires assumptions about processes no one has witnessed. The official risk assessment from the USGS is carefully worded. No eruption is expected in the foreseeable future. But foreseeable is doing heavy lifting there. It means within the span of current monitoring capabilities, current political will, current funding cycles. The truth is simpler and harder. No one knows. The systems driving Yellowstone operate on timescales from hours to hundreds of thousands of years, and we've been watching for less than a century, because the only certainty is that Yellowstone will erupt again. The inevitability. The caldera sits above a mantle plume, a column of superheated rock rising from 1,800 kilometres below the surface. That plume has been feeding magma into the crust for 17 million years, carving a trail of calderas across Idaho and into Wyoming as the North American plate drifts southwest. Yellowstone itself has produced 3 super eruptions and dozens of smaller events. The magma reservoir is still there, still being recharged, still thermally active. The system hasn't gone dormant. It's between eruptions, the way a heart is between beats. Given enough time, another eruption is geologically certain. The question isn't if, it's when. Next decade, next millennium, 100,000 years from now. The magma doesn't care about human timescales. Statistically, Yellowstone erupts every 600,000 to 800,000 years on average. The last super eruption was 640,000 years ago, which sounds ominous until you remember that averages are not schedules. Volcanoes don't run on clocks, and the type of eruption matters as much as the timing. The eruption spectrum. Not all eruptions are created equal. A super eruption ejects more than 1,000 cubic kilometres of material, collapses the magma chamber into a new caldera, and alters the climate across continents. Yellowstone has done this 3 times. The Huckleberry Ridge eruption 2.1 million years ago released 2,500 cubic kilometres, twice the volume of Mount Everest. A Plinian eruption is smaller, 1 to 10 cubic kilometres, but still catastrophic on a regional scale. Ash columns reach the stratosphere, lahars flood river valleys, and ashfall blankets hundreds of kilometres. Mount St. Helens in 1980 ejected 1 cubic kilometre. Then there are lava flows, effusive eruptions where magma oozes to the surface and spreads slowly across the landscape. No explosion, no ash cloud, just molten rock advancing at walking speed. Of Yellowstone's last 70 eruptions, all but 3 were lava flows. The odds overwhelmingly favour a small eruption over a large one, a localised lava flow that destroys a few square kilometres of forest and closes park roads. geologically minor, economically manageable, photographable from a safe distance. But it's the small eruptions nobody prepares for. The lava flow scenario. The fissure opens quietly. No explosion, no column of ash. Rhyolitic magma oozes out like toothpaste from a tube, viscous and glowing, advancing across the ground at a walking pace. Over days, it slows to meters per hour. Over weeks, centimeters. The flow spreads outward, a river of molten glass creeping through lodgepole pine, incinerating everything it touches, leaving behind a black expanse of cooled rock. A single lava flow could cover 40 square miles over 6 months. Roads buried, infrastructure destroyed, but almost no ash plume. Seismic monitoring would give days of warning. Evacuation routes would stay open. Mount St. Helens in 1980 killed 57 people. A Yellowstone lava flow detected early might kill none. What would devastate the country is the eruption everyone fears. The super eruption impact. 1,000 cubic kilometers of magma exits the chamber in hours. The caldera collapses inward, dropping hundreds of meters. The eruption column reaches 25 miles into the stratosphere, punching through the jet stream. Ash blankets Wyoming under 3 meters. Montana, Nebraska. The Dakotas disappear under deposits thick enough to collapse roofs and bury highways. Air travel across North America stops. No flights for months, maybe years. Crops fail across the Midwest. Wheat, corn, soy, all buried or poisoned by fluorine-laced ash. Global temperatures drop 1 to 3 degrees Celsius as sulfur aerosols reflect sunlight. Monsoons weaken. Growing seasons shorten worldwide. Not extinction, not the end of civilization, but famine, displacement, economic collapse on a scale no modern government has planned for. And the ashfall map is more complicated than most people realize. The ash distribution. The plume doesn't spread evenly. Prevailing westerlies catch the column and bend it east-southeast, funneling the heaviest ash into a narrow corridor. Wyoming sees 1 meter at 100 miles from the caldera. Montana and Nebraska, 10 centimeters at 500 miles. But measurable deposits reach the Gulf Coast. Trace ash falls on the Atlantic seaboard. Even 3 centimeters is enough to collapse a flat roof, contaminate a water supply, clog an air filter. Cities 1,000 miles downwind would face infrastructure failure without a single tremor. The thickness drops exponentially with distance, but the footprint is continental. Airports in Chicago, Dallas, Atlanta would close. Interstates would become impassable. The entire eastern power grid would face transformer failure from conductive ash-shorting high-voltage lines. And every simulation shows the same pattern. The ash reaches furthest where the population density is highest. But the ash itself isn't the deadliest part. The respiratory hazard. Volcanic ash isn't soft. It's pulverized glass and rock, microscopic shards with jagged edges that abrade lung tissue on contact. A single breath in heavy ashfall can feel like inhaling sandpaper. The particles lodge deep in the alveoli, where oxygen transfers into the bloodstream. Over weeks and months, silicosis sets in. Scar tissue replaces healthy lung, and breathing becomes a struggle that doesn't end. When Nevado del Ruiz erupted in 1985, ashfall across Colombia sickened thousands, overwhelming clinics 100 miles from the crater. A Yellowstone supereruption would create a respiratory crisis across 10 states simultaneously. Every hospital from Montana to Texas would fill within 48 hours, and the ash would keep falling for days. And the infrastructure damage would begin before the ash even settled. The power grid. Dry ash is abrasive. Wet ash conducts electricity. Both properties are catastrophic for power grids. When ash blankets transmission lines and gets wet from rain or morning dew, it creates conductive bridges between high-voltage conductors. Transformers short out. Substations arc and fail. The 2010 Eyjafjallajökull eruption in Iceland grounded air travel across Europe, but the ash layer was measured in millimetres. Yellowstone would deposit 10 centimetres or more across the Midwest. Turbines at coal and gas plants would choke on airborne grit within hours. Cooling systems would clog. Even undamaged plants couldn't transmit power through a compromised grid. The blackout zone would span from the Rockies to the Great Lakes, and repairs would take weeks in areas where ash had to be cleared first, months where equipment needed replacement. But what comes after the immediate crisis is the part nobody wants to model. The volcanic winter. Sulfur dioxide doesn't fall with the ash. It rises into the stratosphere, 15 kilometres up, where it reacts with water vapour to form sulfuric acid aerosols. These droplets are tiny, reflective, and they stay aloft for years. They scatter incoming sunlight back into space before it can warm the surface. Global temperatures drop. When Tambora erupted in 1815, it ejected 60 million tonnes of sulfur dioxide. The following year, 1816, became known as the year without a summer. Snow fell in June across New England, crops failed across Europe and Asia, famine followed. A Yellowstone supereruption would inject 5 times that amount into the stratosphere. Climate models predict 2 to 3 years of cooling, with average temperatures dropping 1.5 degrees Celsius to 3 degrees Celsius across the Northern Hemisphere. Growing seasons would shrink by 30 to 50 days. Wheat, corn and rice harvests would collapse in the same year, across multiple continents. And the historical record shows it's happened at Yellowstone before. The Huckleberry Ridge climate. The Huckleberry Ridge eruption 2.1 million years ago left its signature in ice cores drilled from Greenland, 4,000 miles away. A sulfate spike appears in the layers dating to that year, followed by a temperature drop of 2 to 3 degrees Celsius preserved in oxygen isotopes. The cooling lasted 1 to 3 years before the atmosphere cleared. Separating the eruption's impact from the broader Ice Age climate is tricky. Earth was already cycling through glacial periods, and Yellowstone's blast coincided with one of those shifts. But the immediate effect was clear. Volcanic winter descended across the Northern Hemisphere. Lakes froze earlier, and ecosystems collapsed under the sudden cold. Ash blanketed the western half of North America in a layer thick enough to bury small animals. Rivers choked with sediment, forests died standing, and daylight dimmed for months. What surprised geologists was how quickly life returned. The recovery pattern. Volcanic ash weathers into some of the most fertile soil on Earth. Within 20 to 30 years, the silica and minerals break down under rain and frost, releasing phosphorus, potassium, and trace elements. Pioneer grasses and shrubs colonize the grey wasteland first, their roots cracking the compacted ash into workable earth. Forests return within 200 to 500 years, slow at first, then accelerating as topsoil deepens. Yellowstone's current landscape, the geysers and lodgepole pines and bison herds, sits atop 640,000 years of recovery from the last eruption. The ecosystem has died and been reborn 3 times. Each caldera becomes a cradle for new life. The heat source that destroyed the old world warms the groundwater, powers the hydrothermal systems, and drives the cycles that make Yellowstone what it is today. But the question everyone wants answered is whether we would see the warning signs. The precursor timeline. Before a supereruption, the precursors would escalate over days to weeks, not months. Seismic swarms would shift from background noise to thousands of earthquakes per day, some magnitude 6 or higher. Ground deformation would accelerate from centimetres per year to metres per week, cracking roads and draining lakes. Gas emissions would spike. Sulfur dioxide and carbon dioxide would pour from new fissures at rates measurable in thousands of tonnes per day, choking anyone downwind. Geysers would stop erupting or shift their schedules as subsurface plumbing rearranged. At night, thermal cameras might catch a glow from magma rising close to the surface. The final escalation would be unambiguous. Continuous ground shaking, visible rifts opening across the caldera floor, steam blasts throwing rock and mud into the air. From that point, you'd have hours to days before the crust fails and the eruption begins. And that short warning window is exactly what emergency planners are preparing for. The evacuation problem. Yellowstone National Park sees 4 million visitors every year. On a busy summer day, more than 30,000 people are scattered across the caldera, hiking trails, watching geysers, waiting in traffic near Old Faithful. 2 main highways thread through the park. The roads are narrow, winding through mountain passes that close under snow from October to May. In summer, a single accident can back up traffic for miles. Emergency planners have run the numbers. A full evacuation of the park would take 8 to 12 hours under ideal conditions, assuming everyone moves at once, no one panics, and the roads stay open. If precursors give you only hours of warning, thousands would still be inside when the eruption begins. But the evacuation zone extends far beyond the park. The impact radius. Within 60 miles of the caldera, pyroclastic flows would scour the landscape at 450 miles per hour, incinerating everything in their path. Ash would fall so thick the sky would go dark. Survival in that zone is measured in minutes. Out to 300 miles, ash accumulation would clog engines, collapse roofs under the weight, render roads impassable. A 6-inch layer is enough to make interstate highways unusable. Cities like Bozeman, Billings, Jackson Hole, and Idaho Falls sit inside that radius. That's over 500,000 people who would need to move before the ash begins to fall. Not days after, not during. Before. And ash travels faster than evacuation convoys. And the federal response plan is still evolving. The FEMA plan. In 2016, FEMA, the USGS, the National Park Service and state emergency agencies ran a tabletop exercise. They wargamed a Yellowstone supereruption from first tremor to federal response. The scenario assumed a week of escalating precursors, then the eruption itself. The outcome was stark. Current state and local resources could not handle mass evacuation from a 300-mile zone. Ash cleanup would overwhelm municipal infrastructure. The response would require a federal emergency declaration within hours, military airlift for medical evacuations, and Army Corps of Engineers deploying heavy equipment to clear roads while ash was still falling. The plan exists on paper now. Coordination protocols, supply caches, designated staging areas. But it's never been tested at scale, and it hinges on one assumption, that the monitoring network gives enough advance notice to mobilise. But the plan assumes we get the warning right, the false alarm risk, because every warning carries a cost. Evacuate 3 million people from the caldera zone, shut down highways, empty hospitals, and you've spent $18 billion before the first ash falls. If nothing happens, you've burned public trust in a system that might need to issue the same warning again in 5 years. Campi Flegrei, outside Naples, has lived this loop since 1982. Ground rises 6 centimetres, seismicity climbs, the alert level goes orange. Businesses close, property values collapse. Then the swarm stops, the ground settles, and the cycle resets. 40 years of crying wolf, and the volcano still hasn't erupted. At Yellowstone, the dilemma sharpens. Issue the evacuation order too late, and you strand millions on roads already choked with traffic. Issue it too early, based on ambiguous seismicity or a single GPS spike, and the next time the ground shakes, no one listens. The forecaster stands at the edge of certainty, watching data streams that could mean everything or nothing. What comes next is the technology that might solve that problem. The AI models. In 2024, Yellowstone became one of the first volcanoes monitored by a machine learning system trained on 30 years of global seismic data. The algorithm doesn't understand magma or fault mechanics. It recognizes patterns, correlations in waveform shape and frequency distribution that preceded eruptions at Mount St. Helens, Pinatubo, Kilauea. The system runs continuously, ingesting real-time seismograms from 450 stations across the caldera. When it detects an anomaly, a sequence of tremors that diverges from baseline noise by more than 3 standard deviations, it flags the event and ranks its similarity to known precursors. A score above 0.7 triggers an alert to USGS analysts. On December 3, 2024, seismometers beneath Norris Geyser Basin began recording faint oscillations at 1.8 Hz, too subtle for threshold-based alarms to catch. The AI flagged the pattern at 4:12 a.m., 11 hours before the tremor intensified enough for human analysts to notice it. By the time the swarm peaked at magnitude 4.1, the model had already elevated the precursor score to 0.82, and the system flagged the December 2024 tremor 11 hours before it began. The prediction paradox. But the algorithm can't tell you what happens next. It knows the tremor is unusual, that its signature resembles patterns seen before magma pushed into shallow crust at other volcanoes. It cannot tell you whether that magma will erupt, stall at 8 kilometers depth and crystallize over centuries, or drain back into the chamber and leave nothing but cooling rock. The December swarm lasted 36 hours, then stopped. GPS stations recorded 1.2 centimeters of uplift, then held steady. Gas emissions from Norris spiked briefly, CO2 climbing to 480 parts per million, before dropping back to baseline. The AI flagged all of it, assigned high anomaly scores, and offered no interpretation. You can train a model to recognize the warning signs. You cannot train it to know which warnings matter. Yellowstone has entered periods of elevated seismicity 9 times since 2000, each time raising the same question: is this the one? The machine sees the data with perfect clarity, faster than any human team could process it. It still doesn't know the answer, because even with perfect data, Yellowstone remains unpredictable. The chaotic system. Magma chambers are chaotic systems in the mathematical sense. A small change in initial conditions, a shift in temperature by a few degrees, a pocket of gas migrating through the melt, can send the entire system down a completely different path. An intrusion of fresh magma can freeze harmlessly into the surrounding rock. It can stall, crystallize, and go quiet. Or it can trigger a cascade, fracturing the crust above, mobilizing older magma, opening pathways that didn't exist moments before. The difference between those outcomes depends on variables we can't directly measure. The distribution of melt versus crystal mush at depth, the permeability of fracture networks threading through the chamber, the exact chemistry and gas content of the rising material. Forecasting requires data we don't have, from places we can't reach. But the current phase might give scientists the data they've been missing. The living laboratory. The 20/24 and 20/25 unrest episodes are rare gifts. Yellowstone is broadcasting its deep processes in real time, its seismic signature changing week by week, its surface deforming in ways that reveal the geometry of what's happening below. Researchers are watching magma dynamics that few ever witness at this scale. Every earthquake cluster refines the velocity models. Every millimeter of uplift constrains the source depth. Every gas measurement adds a data point to systems that have operated in shadow for centuries. The swarms aren't a threat in themselves. They're a window, a chance to watch a supervolcano's plumbing adjust under stress, to see how the crust responds when deep reservoirs shift, to test whether the models built on Icelandic and Hawaiian volcanoes hold true for something this immense. And what they're learning is changing the picture of what Yellowstone actually is. The new phase. The synthesis of all those signals points to a single interpretation. Yellowstone has entered a phase of deep magmatic intrusion. Melt from the lower reservoir 20 to 50 kilometres down is ascending toward the upper chamber. This process hasn't been clearly documented in the modern monitoring era. The caldera has inflated and deflated before, responding to hydrothermal pressure and shallow magma movement. But this is different. The seismicity is deeper. The deformation patterns suggest active transport, not passive accumulation. It doesn't mean eruption is imminent. The system could restabilize in months, years, decades. The intrusion could freeze before it reaches the surface, or the unrest could continue for centuries, the caldera breathing in slow motion, rising and falling as magma ebbs and flows beneath. What it means is that Yellowstone is no longer dormant in the way it was. It's transitioning from a passive cycle of inflation and deflation into something more dynamic. The restlessness isn't a countdown. It's a shift in state, a fundamental change in how the system is behaving, and scientists are watching it unfold in real time. The human question. Every morning, a team of scientists in Menlo Park, California, logs into a monitoring dashboard that tracks Yellowstone's vital signs. They review seismograms from the night before, check GPS stations for millimetre shifts in the caldera floor, scan gas readings from thermal vents. It's routine work, meticulous and quiet, the kind that demands years of training to interpret correctly. But beneath the routine lies a weight that few other scientific disciplines carry. These researchers are watching a system that could remain dormant for 100,000 years, or begin its next eruption sequence within their lifetimes. The probability is vanishingly small, but the consequences are so large that the mathematics of risk break down into something closer to philosophy. In Gardiner, Montana, 12 kilometres from the caldera's northern edge, families raise children, open businesses, plan retirements. Park rangers give tours to 4 million visitors each year, standing on ground that rises and falls by centimetres annually. They know the statistics, they've read the reports, and they choose to stay. It's a strange bargain, living alongside a feature that operates on geological time, while human lives flicker past in decades. The monitoring continues, the data accumulates, the models refine their predictions by fractions of a percent. But there is one measurement that ties all the others together, one number that summarizes where Yellowstone stands right now. The Unrest Index. In 2018, the USGS Volcano Hazards Program formalized what's called the Volcanic Unrest Index, a composite score built from 4 primary data streams. Seismicity contributes 30%, ground deformation 25%, gas emissions 25%, and thermal anomalies 20%. The scale runs from 0, representing complete background condition, to 100, indicating imminent eruption. Yellowstone's baseline, measured across the decades of relative calm between 1985 and 2004, sits at 8. During the 2014 swarm, when 4,000 earthquakes rattled the caldera over 6 weeks, the index briefly touched 23. The Norris Geyser Basin disturbance of 2020, with its sharp CO2 spike and localized uplift, pushed the number to 19 for 3 months before settling back. Today, as of December 2025, Yellowstone registers a 14. That's elevated, measurably above the long-term average, but still in what researchers classify as Level 1 unrest, minor deviation from background. Level 2, moderate unrest requiring increased monitoring, begins at 35. Level 3, the threshold where emergency planning activates, starts at 60. The new phase the title references is real. It's visible in the data, quantified in that index, a sustained shift upward that wasn't present a decade ago. But it's also 21 points below the line where scientists would recommend any change in public policy or park access. And that index leads to a question no model can answer for us. The choice ahead. The question isn't whether Yellowstone will erupt again. It will, almost certainly. Though the timeline stretches beyond any horizon human civilization can meaningfully plan for. The question is how we choose to hold that knowledge, what resources we direct toward monitoring a threat defined by its improbability and its scale. The current monitoring network costs $3.02 million annually to maintain. Expanding it to the level seismologists consider ideal, with 200 additional GPS stations and a denser seismometer grid would require $47 million upfront and $8 million per year. The AI prediction models, still in development, need another $12 million in funding to reach operational capability. Against that sits a hazard with a 1 in 730,000 annual probability, a number so small it resists intuition. We spend more preparing for asteroid impacts, which carry roughly the same odds. We spend vastly more on earthquake retrofitting in cities where the risk, while more frequent, affects fewer people. There's no correct answer, no equation that balances the budget against the lives at stake in a scenario that may never occur. The choice sits in the gap between what we can predict and what we can prevent, between the deep time the caldera operates on and the quarterly budgets that fund the work. The monitoring continues, the index ticks upward by fractions, and the caldera breathes beneath the snow. The caldera at night. You stand at the edge of the caldera after dark, the air sharp and cold, your breath visible in the starlight. Behind you, Old Faithful breathes on its schedule, steam rising pale against the black. The seismometers record in silence. The GPS receivers log their millimeter shifts and the gas sensors sample the wind. Above, the Milky Way arcs across a sky undimmed by cities, the same stars that watched the Huckleberry Ridge eruption 2.1 million years ago. The ground beneath your feet has risen 10 centimeters since 2004, subsided, risen again. The helium ratio holds steady at 16. The swarms come and go, and the magma lens sits 8 kilometers down, neither growing nor cooling fast enough to matter on human timescales. Yellowstone remains restless. The unrest persists at low levels, below the thresholds that would trigger advisories, above the baseline that defined the caldera a century ago. The story continues in deep time, indifferent to the instruments and the questions and the models we build to understand it. We are witnesses passing through, 80 years against 2 million, recording what we can, while the caldera endures. The monitoring continues. If this kind of deep time storytelling helps you see the world differently, there are more waiting. The caldera breathes on.